All right, now for the last type of optimization with a box that we're going to talk about. This is going to be the type of problem where you cut something out of the corners of a box and then fold that up. So here's what it's going to look like. So basically you cut the corners out, and then these corners are all going to be the height. So we can list the dimensions of them as h by h, because when these get folded up, they're going to be the height. So our problem gives us that it's 50 by 20. So we'll call this 50 centimeters, and this part 20 centimeters. That makes this part 20 minus 2h centimeters, and it makes this part 50 minus 2h centimeters. So now our formula for volume is going to be 20 minus 2h times 50 minus 2h times h, right? That's an adaptation of length times width times height. So that's how we're going to get our formula for that. So then we need to multiply this out and simplify it. So first, let's do FOIL with these two terms. And we're going to get 100 minus 40h minus 100h plus 4h squared, all times h. So we are going to get 4h cubed minus 140h squared plus 100h. 1,000h, right? Because we're doing 20 times 50, so that should be 1,000h. All right, so now we're going to want to take the derivative of this volume formula. So we're going to get 12h squared minus 280h plus 1,000. And we need to find the zeros of this, right? Because in order to make a sign chart for our first derivative to figure out where we're increasing and decreasing, and therefore where we have a max or a min, we need to set it equal to 0. So 0 equals 12h squared minus 280h plus 1,000. And this is where the quadratic formula comes into play. So for these type of problems where you're folding the corners up, you sometimes are going to have to use the quadratic formula. So in this case, we have negative b. So remember, this is our a, this is our b, and this is our c. And that's going to be put in the form, and it's going to look like this. So just as kind of a spoiler, this is going to simplify to 35 plus or minus 5 times the square root of 19 all over 3. So this is going to give us two values, and I think on a quiz or an exam you'd probably be dealing with something a lot easier to work with than this. You probably wouldn't be expected to simplify this by hand. I know I used a calculator for it. All right, so, and this is going to give you two possible points of where h equals 0. Not h equals 0, but critical points, right? So 35 plus 5 square root 19 over 3, and then 35 minus 5 square root 19 over 3. So we're going to go ahead and make a sign chart with those two values. First, we're going to start with 35 minus 5 square root 19 over 3, and then 35 plus 5 square root 19 divided by 3. So now we're going to plug in values to see if we get positive or negative. So if we plug in something on this interval into here, this term is always going to be positive. That is going to be a negative, right? So then negative and a negative. So this is going to be negative, this is going to be positive, and then this is going to be negative. So we're going to be increasing on this interval, we're going to be decreasing on this interval, and then we're going to be increasing on this interval. So that means we have a local max here and a local min here. And now we have to go and we have to recall what the problem is asking us for. So we're looking for the maximum volume. So we're looking to maximize volume. So our eyes immediately come to this local max. But unfortunately, we are not able to say that this absolute max is definitely the local max. And that's because we are increasing on this interval over here. So basically it's like if the interval was here to here, we would definitely have an absolute max there. But since we increase from here to infinity, then that leaves some potential for a max being somewhere along this interval. So then what we have to do next is we have to find our absolute max on a closed interval. And if you recall, when we're talking about absolute max on a closed interval, that is going to occur at one of three places. The first is a local max, which we have here. The second is going to be the left endpoint of the closed interval, and the third possibility is the right endpoint of the closed interval. So we have to find our endpoints. So in order to do that, we have to think, what will make this box not a box? So one possibility is if our h's are 0. So if our h's are all 0, then we don't have a height. And if we don't have a height, then we don't have a box. So h equals 0. Alternatively, if we cut a box like this so that the entire side is just consumed by our height, then we also don't have a box. And so we have to look at this 20 minus 2h, because if our h is 10, then we completely eat up this whole side and we don't have a box. So our right endpoint is going to be 10, our left endpoint is going to be 0, and we're going to have our local max. So we can actually test all three of these points. So we have the value of our local max is going to be f of 35 minus 5 root 19 divided by 3. And when we plug that in, just take my word for it, you get 2030.34. So then now we're going to test our left endpoint, v of 0. Oh yeah, I'm sorry, this is not f, this is v. So when we plug in 0 to our v, right here, we get 0, right? Because this h multiplies everything, we get a 0. And then when we plug 10 in to our v, this, we get 4,000, right? Because 10 cubed is 1,000. 1,000 times 4 is 4,000. Minus 140,000 plus 1,000 times 0, or times 10. So this is going to all cancel out and we get 0. So then our v of 10 is going to be equal to 0. So then we need to choose the max between this, and this, and that max is obviously going to be this, right? So we say we have the maximum volume is 2030.34. And let's see, what did the problem ask us for? Determine the height of the box that will give the maximum volume. So we have to plug it back in and we have to find our height. So in order to solve for our height, we are going to grab this and set it equal to 2030.34. And then when you solve for that, take my word for it, you get 4.4018. And that will be our final answer.